First panel, so let's see how it goes. Thanks to the speakers for the talks today. And thanks, that's great. So this should be organic. I have a few questions that we can try to use if there's moments of silence, but otherwise, maybe the first thing we should start with is we've had several discussions already after the talks. So if there's any topic anyone wants to bring up and follow up on, have a bit more discussion, we should entertain that. So feel free to jump in with any topic, including our panelists here. Anything that we discussed already in the questions or during the coffee break that we'd like to follow up on. And the only thing I'll say is if it's directed at a specific person, please say so. Otherwise, we can try to have a few opinions. And panelists, please, if you could keep answers to kind of a couple minutes, that way we can, in the half hour, go through a few questions.
So I want to follow up on something that I think Michael had asked about earlier about data releases and releasing sort of Monte Carlo. And so I want to know where we're going with, especially because people have been looking at the Miniboun data again now, and there have been issues with, certain things that cannot be analyzed because there's one person that knew what this was, and that person is not in science anymore. And so there are issues now with going back to Miniboun data and trying to reanalyze it. And so how are we trying to address this in this generation of experiments so that we don't run into this problem? Let's say 10 years from now, when someone has a good idea that they want to apply to old data.
I mean, there have been a lot of discussions, both like internally on T2K and between experiments on how to deal with this problem. Some experiments, particularly Minerva, have done quite a lot of work on this and even published in papers on how they intend to do it. The essential problem, though, is how to ensure that the systematics that you evaluate at the time of the analysis are relevant for any future user. And there's a risk if you give away too much information, people will use it in a way that's not really appropriate. And so how to not only release the information, which of course is possible, we can release we can release Monte Carlo, we can release like event by event splines of what all the systematics do, with some limitations. But how to ensure that the limitations of those systematics, the inherent limitations, are dealt with or explained in a way that all future users, will firstly respect and secondly understand is very challenging, right? And I think that problem has not been entirely overcome. And I think whatever happens, there will be fairly severe limitations in what can be done with the data if a completely new idea is come up with. Because, at the end of the day, whilst we could release the entire software stack, it wouldn't be useful. Like you could evaluate an entirely new systematic, but I very much doubt people would, or it would be easy to do. I don't know if anyone wants to add to that.
A very short sentence, and Callum covered everything. I think we have definitely learned specifically from the Miniboun experience that the least we should do is also release the covariance matrices. And I think at this point, all experiments, because of that experience, are on the same page, and all data releases would include that. So that's one extreme of the minimal thing that at least we have agreed on. The other extreme was, as Callum was trying to describe, releasing everything, the whole stack. And that would be good in the ideal world scenario, but there are limitations to that. So I think it's good that we had started releasing this, maybe through the work that Minerva is putting in, and maybe talking amongst ourselves, we can figure out another step beyond that at least all experiments can do, and that would be good for the community.
In defense of Miniboun, right, is, one reason why we always talk about what was done on Miniboun and how we're improving it is because Miniboun released so much information about how they did their analysis that people were able to see the problems, whereas for maybe earlier experiments that just wasn't done. So we always talk about the problems with Miniboun, but really it's through their sort of improvements that we were able to start that conversation.
Right, this is not a dig on Miniboom. It's just used it as an example because I've seen it recently. People going back and having issues trying to.
Sure. I mean, I often say things about how it was on Miniboom, and I just wanted to, in defense, I have no skin in that game, but like I wanted to say.
I just want to say
I fully second what you said. So from a theorist and phenomenologist point of view, Miniboom is really doing an amazing job compared to some other experiments. In general, I think the Fermilab experiments are doing a magnificent job in releasing information and being extremely responsive to questions from the theory community.
Oh, okay, thank you. Any other follow-ups from earlier this morning? Or no, were you going to say something? Okay. Any other follow-ups from earlier in the morning?
Oh, I mean, now that we heard both of your talks on NOVA and T2K, we can ask an important question, whether it's redundant to have two long baseline experiments or whether it is informative. And I think the current situation with in the appearance channel already has proven. So you can call it a softball question or not a question at all. But nonetheless, I think this deserves some discussion in view of the planning of future experiments where. No, but I just want to, okay. Don't talk about later. Just talk about now. Just can you discuss the current situation in the long baseline, in the appearance channel in particular, and the global analysis? Maybe you want to say more about the combined analysis that you guys are planning to do.
Yeah, I think I'm sure everyone would agree, and if someone disagrees, let me know that having complementarity is really, really useful. There is, in this business of neutrino experimental physics, there's just so much that we do not know and so many assumptions that go into it. More data is good, number one fact, but I think the ways the analyses are done, the different energy spectrum, the different flux are providing us really valuable insight. And so as someone, in full disclosure, who did their PhD in T2K, and now I'm doing my postdoc in NOVA and Dune, even I learned so much in the process of doing this analysis. And so there is a sociological and analysis development, but I think just the data will bring out complementarity and resolve some degeneracy. So at the moment, it is definitely useful. And I do have some thoughts on why it will remain useful for future experiments, but we'll save that for the next panel.
Mm-hmm.
Yeah, I guess I would reiterate something that Zoya actually said in her talk, that the fact we have two different energy regimes and we're dominated by different cross-sections is very, very important. I mean, there were a lot of questions throughout this morning about cross-section modeling, and that is the issue that keeps me up at night about all these experiments. And so I think having that redundancy is really important. I think also, not just from that sort of practical point of view, but the different setups of the two experiments, which, we're talking only about T2K NOVA right now, nothing else. But having T2K at a short baseline and having NOVA at a longer baseline, so there's an enhancement through the matter effect, which obviously enhances lots of non-standard oscillation scenarios, means that even though they're both going to be statistically limited for pretty much their entire runs, T2K and NOVA, I mean, I think that's fair to say, right? It means we might start getting beyond just measuring the three flavor parameters and maybe come up with interesting things to test for the next generation that we wouldn't have access to with the experiments by themselves.
Maybe one follow-up from me on the specific idea of joint analyses between the two experiments. Is it practical or feasible to see that happening with, for example, common generators to really boost as much as possible the potential for correlations between the experiments? I mean, everything is possible to some extent, but it is something that's practical, I guess.
So when we started the process of joint analysis, conceptually, that would have been the easiest thing to do conceptually. But of course, the limitation in the software stack, as all experimental collaboration are aware of, is just huge. That still remains our North Star goal. I think it's fair to say you won't see it this year. But that is really, really hard. And while it is not off the limits, and it remains, as you said, for all of the reasons that you asked in the question, that it will really help us then figure out the cross-section problem. There will be an attempt, but I think just through the process of this, we are trying to focus on parts and zones that matter and that don't matter. And getting out the first analysis will also help us, maybe instead of going the whole way, are there subcomponents of the models that we can test better and things like that?
Oh, sorry. I'll just quickly add that it's a lot more challenging than simply switching generators. You know, the cross-section model on T2K, I described, I think, in response to Alex's question after my talk, we add a lot of ad hoc parameters, which maybe wouldn't work in a joint fit, right? Like T2K, the behavior, the influence of resonant time production is very much subdominant. So we kind of do some pretty brutal things there that would not be okay to do on Nova. So we'd have to completely reevaluate the way we did. We added those sort of ad hoc improvements or changes to the generators.
Yeah, given how difficult it is to do combined fits, I think as a community, we should keep that in mind for the future, because once there will be Dune and Hyperkamiokande, of course, there will also be joint fits. And now, while the software stack is being developed, now is a good opportunity to keep that in mind from the start and build it in to the extent possible. Since in Dune and Hyperkamiokande, those will be systematics dominated experiments, and then it's even more valuable to have two of them.
Great.
Yeah, just a quick comment on what you mentioned. Can you use the same generator? This is actually a big issue for the entire neutrino community. We were discussing before the Miniboun excess. We need to keep in mind that Miniboun was using a Monte Carlo generator, which was just Miniboun. And we are talking about this excess, and then we, try to translate this effect, this excess to other experiments, but that's an excess with respect to a very specific model, which is not the same that other experiments are using. So I think this story of try to use, common theory base for all the neutrino experiment is a big one. And so goes beyond NOVA and T2K, I think. And this is due to the fact that probably each experiment has developed its own path, but it's something that we should consider very, very seriously, I think, because it's a big issue.
So just the experience of starting to do this joint fit did help us influence, for instance, when we were using the latest Gini model, and while we were going to stick with Gini because of some of the things that Karam described, that our analysis is tuned towards that. But what T2K, the model it has, helped us like, okay, maybe we will use the both near-West model for 2P2H and QE because, and even though it's near-West model, there is still within that, we see differences in implementation, exactly. So my experience has been we speak different languages is how I describe the NOVA T2K cross-section, but we are trying through this process to figure out a common voice and common language for that.
Thanks.
I guess I also, just to add one small thing, I do agree that having common generators is important, but I think that one thing we've learned through various things, not just the joint fit, but trying to extract model independent results, is that focusing on a single generator is very dangerous. And so I think that trying to build in the capabilities to use multiple generators from the start is an important lesson for the future.
Thank you. Next up, maybe something on the short baseline side. Questions? I have an open-ended one we can start with. So for Ornella and Joachim, SPND turns on in a year or so. What are you most excited to, in Ornella's case, I guess, to produce as part of the collaboration?
Yes.
And Joachim, what are you most excited to see like right away?
Yeah, exactly. In fact, I would leave to him, because of course being part of the experiment for me would be the most successful part would be to turn on the experiment, to be able to run in the condition for which the detector has been designed, to see data, calibrate the data as quickly as possible. So I think, and as I said, the interaction with the theorists, I think is crucial. I want this to be an important part of the SBN program for the future. So I will be
Of course, ideally, we want to see a collaboration with infinite people power who's able to analyze, to do all the analysis in a matter of a month. But since that is maybe asking a bit too much, I think one of the most important things I'd like to see is an inclusive single photon analysis. We've seen from Microboom, we've seen amazing single photon results, but these were very much geared towards the delta to gamma background in Miniboun, which in my opinion was of course one of the prime suspects for explaining the excess. Now, since that has not materialized in Microboom, I think it's crucial to see an inclusive single photon analysis, because both within the standard model and outside the standard model, there may be other processes that make single photons to which an analysis geared towards delta to gamma would have relatively low sensitivity, because that analysis, for instance, as far as I understand, uses the invariant mass of the nucleon and the photon as a discriminator. So it only picks up things that have an invariant mass comparing to the compatible with the delta resonance, whereas an inclusive search could do much better. And SBND will have the statistics to do that in a meaningful way. Apart from that, the obvious thing that of course will be done is the new appearance search. So after what we've seen from Microboom, of course, the most likely that will look like the standard model. And then beyond that, I think it will be interesting to target more exotic signatures, like for instance, boosted E+ E- pairs.
Yeah, okay, thanks. All those are great suggestions. And as you said, an inclusive gamma analysis will have a lot of statistics. So this is, I think a very good suggestion. And other, boosted electrons like signature is something that we are trying to study and see the sensitivity of the experiment. But yeah.
You should ask the audience if any of
Yeah, if you have wonderful idea, make suggestion. I was trying to say we need suggestions from the community.
Yeah, I agree with everything Joachim said. The single photon, I guess the inclusive one probably won't be that different from the existing single photon with no protons. I guess, yeah, I'm wondering how different that search would be. Because I know people are also doing coherent photon emission, so that would be nuclear coherent emission instead of the delta.
I think it will be different because it will have much more statistics than in Microboom, right?
Oh, I mean, yes, but also more backgrounds, no? My question is how much do we think we will improve on that channel with respect to Microboom? Given that the backgrounds are pretty large for the single photon in Microboom already.
Now, my naive hope would be that with the increased statistics in SBND and the possibility to have different control regions to tackle those backgrounds, it will be easier to understand these backgrounds and therefore isolate the signal in a better way. So it will, of course, not be completely orthogonal to what Microboom did, but it will build upon this and improve on it with the power of a high statistics measurement.
That makes sense.
Yeah, and I think just to add one thing, regardless of the detector you're looking at, I think there's actually improvements on the tools being used that are coming in all the time. So kind of what Ornella showed today is kind of what's come out of this first round of analysis from Microboom, leveraging years of development from Microboom and other experiments, Argonaut, Icarus, but beyond, in addition to more detectors with more statistics, there's also further improvements that I think would complement those searches quite a bit.
Yeah, exactly. We are, as a community, we want to work on the reconstruction of relatively low energy electromagnetic showers in general. Because this is certainly an area where improvement in the reconstruction will pay off with more sophisticated measurements. But I have a question for you. What about, I understand where this inclusive gamma analysis is coming from, but naively, I would have started doing, just reconstructing all the events which have electromagnetic showers before discriminating gamma from electrons, and make a comparison of just that with what we have from Monte Carlos, from all the possible sources of single electromagnetic showers, not necessarily applying the electron gamma separation at the beginning. So do a more inclusive one. What do you think about that?
So this would basically mean lumping together the single electron and the single photon. So these are the only things I can imagine that make an electromagnetic shower. But my understanding is it is relatively easy to do this discrimination. So why not do it from the start? And then if someone wants to see an inclusive analysis, it's easy to throw them back together again. With an inclusive one, yeah, I see where you're going, because this would be like the most direct test of the Miniboun access. So the question is if an analysis that targets single electrons plus an analysis that targets single photons would not cover all of that. But of course, there will be slightly different cuts, and there's always the possibility that something is missed. So yeah, maybe that could be an even earlier step than yeah, and like the most direct test of Miniboun. No, I agree. That's a good point.
So I have to follow up on that comment, and I think one way to pose this problem is, so we basically need to know what Miniboun saw, right? Just what is it that was that signal? I think the idea that it's somehow like a 5 sigma fluctuation that we can, set aside. That's not a serious explanation. So then the question is like, what's the systematic program for the next several years to try to identify what that signal was? There's a sort of this misperception that's saying, oh, microboom disproved Miniboun or something like that, which goes around the community, which does a lot of harm. But like, how do we systematically approach this big task to sort of unravel what Miniboun saw? And maybe like another question, but it may be related. So right now you have these 3 analyses. They're very different in techniques. They look at different modes. So going forward, I guess there should be analysis where you use different reconstruction techniques for the same event topologies to see how they perform relative to each other. So is that something that Microboon itself can do, or is this something that Icarus would start doing, or SPNG from when that turns on? Like, what's the prospect of the next generation of analysis where you combine different approaches and cross-check? There may be 2 different issues.
Yeah, I think for Microboon, I will leave to David to answer what the next phase will be, because we need to keep in mind that directly testing the low energy excess is a job that Microboon was designed to do. The short baseline program is not designed to test directly Miniboun. It's was designed to test the sterile neutrino hypothesis, which is different. So we are not thinking to do the analysis exactly in the way Microboon is doing, which is just testing this. The short baseline program is designed to do near-far comparison and see if you see an effect on that specific hypothesis or some of the specific hypotheses. And then in parallel, as I said, do other type of measurements for different, alternative explanation. So the SPM program is not thinking to redo exactly what Microboon is doing. So I think your question, if you are thinking to just directly test Miniboun, is more addressed to Microboon than to the SPM program. In SPM, of course, Icarus could do something but you know, the SBN program has been designed as near far comparison for what concerns, you know, an oscillation hypothesis. So it's not designed to test Miniboun directly. This doesn't mean that we can do what, for example, was suggested before, this single gamma analysis we can do just in SPND, but it's not, you know, but the SPN program has been designed to do differently, near far comparison to test, you know, the scenario of the oscillation hypothesis differently.
I can say a couple of words, but maybe someone else on the panel wants to say before we move on to a T2K Nova question. Okay, so I'll just say two words quickly. In some sense, my answer has already been touched on by Joachim and Ornella in two different points. One is more inclusive searches, single photons, or even just single electromagnetic showers. I think that's key because yes, otherwise I agree. You can't just say we've disproven something if we haven't kind of looked under every rock. But the other part is the less pretty part is what Ornella touched on, the difference in generators being used by different experiments. It's just not as direct a comparison as a headline may make it seem, because the two experiments use different generators, and undoing that or solving that is unfortunately a larger problem than you might hope. But on just the current program on its own, more inclusive searches is definitely the way to go and the way we're hoping to move towards. Okay, yeah, let's go ahead.
Another question related about the solve baseline program.
Okay.
So there are, apart from appearance, there are other results like disappearance, muon disappearance, that are very strong. For instance, in the case of MINOS. Is there any plan just to test the result of MINOS, in particular for high masses, in the solve baseline program? Is there any idea to redo this analysis?
You mean the muon disappearance?
Yes. Exactly.
Yeah, I showed you the sensitivity, and I think one of the big strengths of the SPM program is exactly to be able to do appearance and disappearance in the same program with the same detector. And if you see an appearance, you should see the equivalent amount of disappearance in order for this to be an oscillation, right? So this is exactly what we want to do, and the sensitivity, I showed you what the sensitivity is, and this is the way in which we want to do the sterile neutrino, the oscillation part of the analysis. By doing appearance and disappearance, we are even, I showed you the two sensitivity shown independently. We are now working on analysis that will do a combined analysis of appearance and disappearance, because the two, they should talk each other. They are not independent. So if it is an oscillation, this is why we always say the SPN program in this respect, and in this scenario, there could be several, but in this scenario, it's really, the ultimate experiment that you want to do, because probably if you don't see anything there, at least some part of the scenarios are not there. So that's.
I don't remember the range of masses that you were considering, but I mean, you are planning to go to hundreds of masses of EV, because this is one of the sensitivities of MINOS is, straightforward. So the idea is to go to 10 to the 2 EV, or even 10 to the 3 or so. That's the idea. Extend to very high masses in the case of.
Very high mass.
Yes, exactly.
Delta M square, you mean?
Yes, exactly.
Yeah, this is, the near detector is the one that allows you to cover this region. And the prism characteristic that I was showing before is exactly in that region, give you more sensitivity, because it's the near detector in which you gain in sensitivity with that. So the sensitivity, actually, when you include these characteristics, they push a limit in exactly that region.
Okay.
So one quick comment from Joachim, and then we'll end up with a question back to TK.
Yeah, actually a follow-up on the muon disappearance. To what extent can a muon disappearance measurement in SBND, in the whole SBN program, be so much better than the limits we have from IceCube and MINOS, since after all, this is a measurement that will be dominated by the systematics with the beam, especially in the high delta M square region. So how far can we actually go beyond the limits that we already have? Because on the other hand, I think it would be great if we could go beyond, because even if this is not an oscillation, most of the BSM models that aim to explain the Miniboun anomaly predict some level of muon disappearance, maybe a bit less than an oscillation model. Because in an oscillation model, the appearance signal is suppressed by u mu force squared times UE force squared. In many of the other scenarios, it's just suppressed by u mu force squared. So you can live with a smaller u mu force squared, but it can't be zero. So if the improvement was possible there, that would be great, but I'm not sure to what extent that is feasible.
You know, what I showed there are the sensitivity that you can reach. So regions that are not covered, I don't see how you could improve. They are what they are. So that's the type of measurement that you can do.
Okay.
I don't think there is a way to improve. Yeah.
So on the topic of oscillation, going back to long baseline, now with T2K and NOVA as back to friendly competitors. So you both mentioned kind of new things that have come into these analyses, whether it's flux constraints, new ways to constrain detector systematics. So it's an open-ended question on kind of what we should be looking out for in the coming years, even in terms of kind of areas where really you'll be pushing the boundary to improve on your systematics and therefore the limits that you can set. So what should we be excited for moving forward?
Okay, well, for T2K, the obvious two things to point out are the gadolinium doping at super K, which will give us, sensitivity to neutrons, which will allow us to disentangle wrong sign, right sign background, particularly in anti-neutrino enhanced mode. We also, the new the ND280 upgrade is specifically designed to fill in some areas where we had problems in the current round of analysis, right? Like it's specifically designed to give us acceptance in regions that the near detector was not doing great at before. So we'll do much better at having something like 4-pi acceptance for a lot of the channels we're using. So those are the sort of planned improvements. I think that something that I hope will happen, but there's maybe a less clear path to going into a public oscillation analysis, is if we can improve our model of pion production to the extent that we trust it enough to include multi-ring samples, right? So we
as a channel in the fit.
Yeah, so we have the one-ring samples, which are QE dominated, and we have the decay electron sample, so we do have pion production, but below threshold. We don't care really about the kinematics of pion production, except how it migrates above and below that Cherenkov threshold. But if we could build confidence in our pion production model to the extent that we were happy to include two-ring samples where we have a pion above Cherenkov threshold, which would mean that we would need to be able to model the systematic, like cross-section modeling systematics on the pion kinematic spectrum. Because we have the data at the near detector to deal with that, we have the samples, but we don't use them because we're concerned about the modeling. And so overcoming that, I think, would be great, because we would, would be able to use a large fraction of our data that we don't currently use. And, it would also add an additional sort of capability because it's higher energy.
Cool. Yeah, so I think in your question, you specifically mentioned systematics, and I will talk about that. But I think Callum mentioned in passing before that how most likely NOVA and T2K both by 2026 is when our planned run would still be statistics limited. So one thing that NOVA is trying to focus on, so because we are a relatively newer experiment as compared to T2K, our new E selections were trying to be mostly conservative. Like initially it was really conservative, trying to get as pure samples as before. Then we added some extra, what we call the peripheral samples, especially which comes from the periphery of the detector, where there is slightly more cosmic background. But one thing they're trying to do is go back and really look at where are we losing these new E events in the detector. We have like 40 to 50% efficiency. And if we can really push that and with the same amount of data already collected, really increase our statistics. So still focusing and aiming on hammering that statistics is still a part of the effort. And if we are able to really increase our statistics, that will help better precision. Going onto systematics, as I showed in the detector, systematic is really dominant. And for that, the test stream program, the NOVA test stream program, is currently running and taking data. We hope the analysis from that comes out in the next couple of years, and we are able to use that to constrain and nail down our detector systematics. I think NOVA is making its own cross-section measurement, but is definitely looking out at other experiments making those measurements, and understanding and constraining cross-section modeling will always be useful for oscillation.
Thanks. Maybe it's about time for lunch. Thanks everyone in the panel. This was, I think, hopefully went well. It was very informative for me. Thank you for participating. Thanks everyone for input, and we'll see you after lunch or at lunch.
Thank you, David. Thank you.